This video will be the second part of the Module 4, Lesson 3 on solving recurrence relations. And in this video, we'll do the exercises in the lecture note. So the first exercise is here on our screen. Solve the following set of recurrence relations and initial conditions. S of k minus 10 s of k minus 1 plus 9 s of k minus 2 equals 0, with initial conditions s of 0 equals 3 and s of 1 equals 11. Now for this first exercise, I just kind of want to remind you that we were guessing that a solution to a recurrence relation like this would have the form b times a to the power k, where b is just some non-zero constant and a is just some non-zero constant. And so we plug this in to our relation. So I'm going to replace s to the power k by b times a to the power k. Then minus 10 sk minus 1 will be minus 10 b times a to the power k minus 1. And plus 9 sk minus 2 plus 9 b times a to the power k minus 2 equal to 0. So I've just substituted my guess into the relation. And then because I know that b times a to the power k is not 0, I can divide all the way through by as many powers of a. So I can divide by b times a to the power k minus 2, because that's what I have in each place, at least that many powers of a. And I'll divide on this side as well. So I've divided the entire equation through by this term, and what's left? In the first place here, I have a squared. Then I have minus 10a plus 9 equals 0. So what I've formed is the characteristic equation of the homogeneous recurrence relation. And remember, this is going to be the process every time. So now I want to factor this equation, or use the quadratic formula to find its roots. In this case, it does factor nicely, so we get a minus 9 times a minus 1 equals 0. So a equals 1, or a equals 9. And these are the characteristic roots of the characteristic equation. So we'll take these and we'll say, then our recurrence relation must be some constant b sub 1 times 1 to the power k plus some other constant b sub 2 times 9 to the power k. I'm using 1 and 9 because these were the characteristic roots. And now I'm ready to use my initial conditions, s of 0 equals 3 and s of 1 equals 11, to solve for b1 and b2. So s of 0 equals 3, and s of 0 is equal to b1 times 1 to the power 0 plus b2 times 9 to the power 0, which is just b1 plus b2. So we have the equation b1 plus b2 equals 3, and I'm going to call this equation 1. Then I have s of 1 equals 11, and s of 1 is b sub 1 times 1 to the power 1 plus b sub 2 times 9 to the power 1, which is b sub 1 plus 9b2. So I have the equation b1 plus 9b2 equals 11, and I'm going to call this equation 2. I need to solve this system of two equations for the two unknowns b1 and b2. So I will take equation 2 and subtract equation 1. So on the left side, that's going to be b1 plus 9b2 minus b1 plus b2. On the right side, 11 minus 3. So you can see I have b1 minus b1, so that will go away. And then I have 9b2 minus b2, so I have 8b2 is equal to 11 minus 3 is 8. And this gives me that b2 is equal to 1. Now I can substitute b2 equals 1 into equation 1. So I'll have b1 plus 1 equals 3. Then b1 equals 2. And finally, I'm ready to put these coefficients back into my recurrence relation. So I said that s of k was equal to b1 times 1 to the power k, so this is 2 times 1 to the power k, plus b2 times 9 to the power k, so this is 1 times 9 to the power k. And I can simplify that just a little bit. 1 to the power k is just 1, so I can write this as 2. I don't need the 1 to the power k. And of course, 1 times 9 to the power k is just 9 to the power k. So I have 2 plus 9 to the power k. And that is the solution, the closed form solution to the recurrence relation. So this is how to solve the homogeneous recurrence relation. In the next example, we'll have a non-homogeneous recurrence relation. So the first step is to examine the homogeneous recurrence relation that accompanies it. So the homogeneous recurrence relation would be s of k minus 5 s of k minus 1 plus 6 s of k minus 2 equal to 0, rather. I'll replace that 2 by 0. And we'll find the characteristic equation in the same way that we did in the first example. Since we know the pattern, I'm just going to go ahead and say that it's going to be a squared minus 5a plus 6 equals 0. I'm just taking these coefficients 1, negative 5, and positive 6. Because k minus 2 is my lowest term, I know that it's a quadratic equation. And again, this equation will factor nicely. If it did not, we could use the quadratic formula to solve it, but this will factor nicely into a minus 2 times a minus 3. And so the characteristic roots are a equals 2 and a equals 3. So the homogeneous solution, I'll use the little h to denote the homogeneous solution, is going to be some coefficient b1 times 2 to the power k plus some coefficient b2 times 3 to the power k. Now I need to find a particular solution. And what we do is we look at the function on the right-hand side, which in this case is a constant function, and we make a guess about the particular solution based off of the function on the right-hand side. So since it is a constant function, I'm going to guess that my particular solution will be a constant function, say d. And then I'm going to plug d into the relation. So I'll replace s of k by d. And minus 5s of k minus 1 is minus 5d. And plus 6s of k minus 2 is plus 6d. And that's equal to 2. I just substituted in my guess at my particular solution. Then I can simplify, and I have 2d equals 2, so d equals 1. Then my general solution to the recurrence relation is going to be the homogeneous solution plus the particular solution. And that's b1 times 2 to the power k plus b2 times 3 to the power k plus the particular solution was 1. And now I'm ready to use my initial conditions, s of 0 equal to -1 and s of 1 equal to 0, to solve for the unknowns b1 and b2. So s of 0 equals -1, and s of 0 is b sub 1 times 2 to the power 0 plus b sub 2 times 3 to the power 0 plus 1. And that's equal to b1 plus b2 plus 1. So from this we obtain the equation b1 plus b2 equals -2. And I'm going to call this equation 1. Then I have s of 1 equals 0, and s of 1 is b1 times 2 to the power 1 plus b2 times 3 to the power 1 plus 1. And that's 2b1 plus 3b2 plus 1. So from this equation, I can obtain 2b1 plus 3b2 equal to -1, and that will be equation 2. So I need to solve this system of two equations for the two unknowns b1 and b2. And I'm going to do this by eliminating the variable b1. So I'll multiply equation 1 by 2 and then subtract it from equation 2. So equation 2 minus 2 times equation 1. On the left-hand side, that should be 2b1 plus 3b2 minus 2b1 plus 2b2. And on the right-hand side, that's -1 minus -4. So canceling 2b1 with minus 2b1. Then I have 3b2 minus 2b1. So that gives me b2 is equal to -1 plus 4 is 3. And now I can use b2 equals 3 in equation 1. So I have b1 plus 3 equals -2. And that tells me that b1 is -5. So now I'm ready to write the solution to the recurrence relation. I had s of k equal to b1 times 2 to the power k. So that's -5 times 2 to the power k plus b2 times 3 to the power k. That's 3 times 3 to the power k plus 1. And the last thing that I can do to simplify just a little bit is say this is -5 times 2 to the power k. Since in the second term the exponential base is 3 and it's multiplied by 3, I can just write this as 3 to the power k plus 1, and then I have plus 1. And this will be the solution to the recurrence relation. Now this third example will be quite a bit more complicated. So I'm going to show you an example of how to do something a little more intricate. But we're going to follow the same process to begin, which is we're going to examine the homogeneous recurrence relation that corresponds to this recurrence relation. So we'll have s of k minus 4s of k minus 1 plus 4s of k minus 2 equal to 0. And it will have the characteristic equation a squared minus 4a plus 4 equal to 0, which again factors nicely and becomes a minus 2 squared equal to 0. So we have a equals 2, and this is a characteristic root of multiplicity 2. So we know from the lecture that we have to take a little bit of an extra step here. When I'm guessing at my homogeneous solution, I'm going to say then the homogeneous solution to the recurrence relation should be something like B10 plus B11k times 2 to the power k. If it were not a root of multiplicity 2, I would just have a coefficient times 2 to the power k. Since it's multiplicity 2, I have to do something like this. Coefficient plus some other coefficient times k, all times 2 to the power k. Now, we'll try to form a particular solution by looking at the function on the right-hand side, which is 3 times k plus 2 to the power k. Now we have one other problem, which is that the root of the characteristic equation matches the exponential base of the exponential function on the side. So we might usually just guess that it would be a constant times 2 to the power k. That would be our guess at the particular solution. But in this case, we have to, again, multiply by k, and not only k, but k squared. So my guess at the particular solution for the term 3 times k, I'll have some constant c0 plus c1 times k. So that's the linear function that I'm guessing because I have a linear function on the right side. And then for the exponential function, I'm going to do d times 2 to the power k, but because I have a matching root of multiplicity 2, I also will multiply k squared. If I had a matching root of multiplicity 1, I would multiply k. If I had a matching root of multiplicity 3, I would multiply k cubed, and so on. So this is my guess at the particular solution. And just like in the last example, the next step will be to substitute this in to the relation. So I'm going to replace s of k by c sub 0 plus c1k plus d k squared 2 to the power k. And then I'm going to replace minus 4 s of k minus 1 by minus 4 c0 minus 4 c1 times k minus 1 minus 4 d times k minus 1 squared times 2 to the k minus 1. And then plus 4 times s of k minus 2, I'll replace by plus 4 c0 plus 4 c1 times k minus 2 plus 4 d times k minus 2 squared times 2 to the k minus 2. And I'm definitely going to get some cancellation, but let me do a little bit more of the distribution before we start trying to cancel things. So I'll have c0 plus c1k plus dk squared times 2 to the power k. Minus 4c0. Then here, I'll distribute minus 4 times c1 times k and minus 4c1 times minus 1. So this will be minus 4c1k plus 4c1. Now here, I want to write this 4 as 2 times 2 so that I can put one of the 2's here with this 2 to the power k minus 1 and make it 2 to the power k. So this is going to become minus 2d times k minus 1 squared times 2 to the power k. So if it's not clear what I did, pause the video now and go back and think about it. But because I had 4 multiplied in front, I just multiplied 2 with 2 to the power k minus 1 to get 2 to the power k, kept the other 2 there. Then I have plus 4c0 plus 4c1k. I'm also going to distribute this 4 to the minus 2, so I'll have minus 8c1. And then I'm going to do the same thing with this 4 that I did. Think of it as 2 times 2, so that I can multiply these 2's here and make this 2 to the power k. So this is just going to be plus d times k minus 2 squared times 2 to the power k. And again, pause the video if you need to make sure you understand. I just multiplied this 4 into my 2 to the power k term. Okay, now I think I'm ready to cancel some things. I see that I have minus 4c0 and plus 4c0. I have minus 4c1k and plus 4c1k. So I'll have c0 is going to stay. And then I have plus 4c1 minus 8c1, so that's minus 4c1 altogether. Then I'll have, so I've taken care of this and this and this. Then I'll have plus c1k. And my other three terms involve d times 2 to the power k. So I'm going to say d times 2 to the power k, and then start a parenthesis. I have k squared. Then I have minus 2 k minus 1 squared. That's this whole term here. And then I have plus k minus 2 squared. So let's see how we can simplify that. The rest of this will remain the same. c0 minus 4c1 plus c1k plus d times 2 to the power k. This will be k squared. Then k1 squared should be k squared, so that's going to be minus 2k squared, minus 2k, so that's going to be plus 4k, and plus 1, so that's going to be minus 2. And then k minus 2 squared should be k squared minus 4k plus 4. And I think I'll get some cancellation there inside the parentheses. It looks like I have k squared is going to cancel k squared plus k squared and minus 2k squared. Then I have plus 4k and minus 4k. So all that's left is times 2, because I have 4 minus 2, so that's times 2 here in the parentheses. And now, one mistake I made when I substituted this in, I should have been writing as equal to 3 times k plus 2 to the power k all along. So I'm just going to write those back in now. In each step, I have this on the right-hand side of my equation. So this is equal to 3 times k plus 2 to the power k. This is equal to 3 times k plus 2 to the power k. And this is equal to 3 times k plus 2 to the power k. And again, that's just this function from the right-hand side. Okay, so now I can see that this equation, in order for the two sides to be equal, I can compare the coefficients. So for example, the coefficient of k is 3, so that tells me right off the bat that c1 should equal 3. In order for the two sides of the equation to be equal, these should be equal. And then I have this term on the left side, C0 minus 4C1, and that doesn't show up on the right side at all, so that should be equal to 0. So C0 minus 4C1 should be equal to 0, but I know a value for C1, so I have C0 minus 4 times 3, just by plugging in C1. That should be equal to 0, because it doesn't show up on the other side. I could have written plus 0 here. And so that tells me that C sub 0 is 12. And then also the coefficient of 2 to the power k should be 1. And here on the left side, I have 2 times d is the coefficient of 2 to the power k. So that tells me that 2 times d equals 1. So d is equal to 1/2. So I found all of the unknowns here in my particular solution. So my particular solution is going to be, I have C0 plus C1k, so that's 12 plus 3k, and then I had d times k squared times 2 to the power k. So this will be plus 1/2 k squared times 2 to the power k. And just to make that look a little bit nicer, instead of 1/2 times 2 to the power k, I'm going to borrow 1, 2 from my 2 to the power k. So I'm going to write this as 12 plus 3k plus k squared times 2 to the power k minus 1. So I just thought of 2 to the power k as 2 to the power k minus 1 times 2. And I took this times 2 and I multiplied it by 1/2 so that I didn't have to write the 1/2 anymore. Okay, so now I have my particular solution. I know my homogeneous solution from before. I'm going to want to write them together. So the solution to the recurrence relation is S of k equal to the homogeneous solution plus the particular solution. And that was B10 plus B11k. Here's my homogeneous solution. Times 2 to the power k plus 12 plus 3k plus k squared times 2 to the power k minus 1. And just to make this look a little bit nicer before we start solving for coefficients, I'm going to combine these like terms, 2 to the power k and k squared 2 to the power k minus 1. I'm going to write this as 2b10 plus 2b11k plus k squared, and everything times 2 to the power k minus 1, plus 12 plus 3k. So again, I just borrowed a multiplier of 2, a power of 2, so that I could make these match and be 2 to the power k minus 1. All right, now I'm ready to use my initial conditions to solve the recurrence relation. So the initial conditions that I had were S of 0 equals 1 and S of 1 equals 1. So if I have S of 0 equal to 1, and S of 0 is 2b10 plus 2b11 times 0 plus 0 squared, and all of that is times 2 to the power 0 minus 1, plus 12 plus 3 times 0, and this is going to be equal to this term is 0, this term is 0, and this term is 0. So what I have here is 2b sub 1 0 times 1/2, because it's 2 to the power negative 1. So this is just b10 plus 12, and that's equal to 1. So from this, I can get an equation, which is b10 equals minus 11. Just subtracting 12 from both sides. 1 minus 12 is negative 11, and b10 plus 12 is b10, once I subtract the 12. Okay, so I found my coefficient b10. Now I can use the other initial condition to get one other equation. S of 1 is equal to 1, and S of 1 is equal to, well, 2 times b10, but I already know my b10, so that's going to be 2 times negative 11 plus 2b11 times 1 plus 1 squared, and all of that is times 2 to the 1 minus 1, then plus 12 plus 3 times 1. So this is minus 22 plus 2b11 plus 1, and that's all multiplied by 2 to the power 0, which is 1. Then plus 12 and plus 3. So this is negative 6 plus 2 b11. So that gives us that 2 b11 is equal to 7. So b11 is equal to 7 over 2. Now I've solved for all of my coefficients, and I'm ready to write my final solution to the recurrence relation. So the final solution is going to be going back to where I was here. That's going to be 2 times b10, so 2 times negative 11, that's negative 22, plus 2 times b11 times k, well, 2 times b11 is 7, so that's plus 7k plus k squared, and that's times 2 to the power k minus 1 plus 12 plus 3k. So that is my final solution to the recurrence relation. If I wanted to write it a little bit differently, I can just, for this term inside the parentheses, write them in descending order, k squared plus 7k minus 22. We're a little bit more used to seeing things written that way. Either form would have been fine, but maybe this is as nice as I could make it look. So this is the final solution to this recurrence relation. Okay, in the next example, I have S of k equals r times S of k minus 1 plus a, where r and a, all I know is that they are greater than or equal to 0, and r is not equal to 1. So I don't have the values for r and a, but I'm just going to treat this exactly the same way. I'm going to first find a homogeneous relation that corresponds. So that would be S of k minus r times S of k minus 1 equal to 0. So you can see I just subtracted this term over to the other side, which left the function on the right-hand side being a constant, but I'm looking at the homogeneous version, so I have equals 0. And then the characteristic equation is just going to be some constant minus r equal to 0. So C equals r. then I get to say that my homogeneous solution has the form some constant times r to the power k. So the root of the characteristic equation was r. And I used c here as my variable because a was already in the problem. In the other problems I've been using a, but a was already in the problem. Okay, so this is the homogeneous solution. Now I need to look for a particular solution, and we've already seen an example where we had a constant on the other side. We just assume that our particular solution is a constant, and we plug it into the relation. So substituting this in, I would replace s of k by d, and then replace s of k minus 1 by d, so minus rd, and that's equal to a, this a. And I want to solve for d, so I'm going to say this is d times 1 minus r is equal to a. So d is equal to a over 1 minus r. Now, my solution to the recurrence relation is going to be the homogeneous solution plus the particular solution. So b times r to the power k plus a over 1 minus r. And I have initial condition s of 0 equals 0. That's going to help me solve for b. So s of 0 equals 0. And s of 0 is equal to b times r to the power 0 plus a over 1 minus r. I want to solve for b, and this is equal to b plus a over 1 minus r. So that's going to give me that b is equal to minus a over 1 minus r. So then the solution to the recurrence relation, the closed form solution, should be minus a over 1 minus r times r to the power k plus a over 1 minus r. So you can see that even though I didn't know the values of a and r, and I still don't know, I just solved it in the same way that I would solve the recurrence relation usually. Okay, so finally let's look at an interest type of problem. If you were to deposit a certain amount of money at the end of each year for a number of years, the sequence of payments would be called an annuity. And we did have this example in the lecture, so if you're not remembering, you can scroll back up to example 1.18, a few pages above. First of all, we're asked to find a closed form expression for the balance or value of an annuity that consists of payments of Q dollars at a rate of interest of I. And in the example above, they used capital letter B for this sequence, B for balance, so they used BK, so that's what I'm going to use here, but we could also use S of K or really any letter that we want. A of K maybe because it's an annuity. Doesn't matter. So B of K, I want the value of the annuity that consists of payments of Q dollars at a rate of interest of I. So I want to do 1 plus my interest rate I times the previous balance and then add the amount I'm depositing each year. And these types of interest problems should look pretty similar to things you would have seen in your college algebra or high school algebra class when you did compound interest and simple interest. This would actually be just simple interest that's only compounded once yearly. But this 1 plus I term is representing, I'm going to keep the balance of the account and I'm going to also add some percentage of the account in interest. And then the Q is how much I'm depositing. So we can use this type of setup to solve interesting problems with real-world applications. So for example, with an interest rate of 12.5%, how much would you need to deposit into an annuity to have a value of $1 million after 18 years? And remember, this Q is the amount I'm depositing every year. So how much would I deposit each year if with interest I want to end up with $1 million after 18 years? So let's start by plugging into our form that we found in part A, this interest rate. So 12.5%, I can write it as 0.125. So 1 plus 0.125, bk minus 1 plus q. And that's equal to, of course, 1.125 times bk minus 1 plus q. So then, if I subtract it over to the other side, if I subtract this 1.125 bk minus 1 term, then it starts to look like a recurrence relation. So I'm going to find the associated homogeneous recurrence relation and follow the same steps we've been doing in the other problems. So that's going to be bk minus 1.125 bk minus 1 equal to, instead of q, 0. And it's going to have characteristic equation. I can go ahead and use a minus 1.125 equal to 0. So a is equal to 1.125. Then that means that the homogeneous solution that I'm going to guess is going to be some constant b times 1.125 to the power k. And then for the particular solution, the function on the right-hand side of the recurrence relation is just the constant q. So for the particular solution, I'm going to say my guess is that it's just a constant. Then plug my constant into the recurrence relation. So I'll replace b of k by d, and I'll replace minus 1.125 b of k minus 1 by minus 1.125 d, and that's equal to q. And I want to solve for this d, so I'm going to factor out d and say this is 1 minus 1.125 times d equal to q. So d is equal to q divided by, and this is negative 0.125. So I'll put the negative there. So I found my d. That means that I can now say the solution to my recurrence relation is going to be this homogeneous solution, b times 1.125 to the power k, plus my particular solution, which is, I'm going to put a minus sign there, minus q over 0.125. And I can use the initial condition to solve for b. Eventually, my goal is to solve for q. So what is my initial condition? Well, my initial condition is that I'm just depositing q dollars. So that's going to be b of 0 equals q. But b of 0 is equal to b times 1.125 to the power 0 minus q over 0.125, which is equal to b minus q over 0.125. And I want to point out here that 0.125, off to the side, 0.125 is equal to 1/8. So this is q over 1/8, which is the same as 8q. So this is equal to b minus 8q. So then I can put this together. I have q is equal to b minus 8q, so b is equal to 9q. Then my recurrence relation has the solution 9q times 1.125 to the power k minus, and again, I'm going to replace this by 8q. So this is the solution to the recurrence relation. Now that I have it, what the question asks me is, what should this q be if after 18 years I want to have $1 million in the account? So I want b of 18 equal to 1 million. And b of 18 is equal to 9 times q times 1.125 to the power 18 minus 8q. So that's equal to, I'm trying to solve for q, so I'm going to factor it out. Q times 9 times 1.125 to the power 18 minus 8. So then q is equal to 1 million divided by 9 times 1.125 to the power 18 minus 8. And we can plug this into a calculator, and we will find that q is going to be, if I round, $14,928.20. So what this says is that if in 18 years I want $1 million in my annuity, then I need to initially invest $14,928.20, and at the end of each year I need to invest that same amount. And then I would have almost $1 million on the nose. Because I had to round a little bit, I think I'd end up with $1,000,030 or something like that. There was one more part of this problem. The payment on a loan is a form of an annuity with the initial value some negative amount, the amount of the loan. And the annuity ends when the value is raised to 0. How much could you borrow if you could afford to pay $5,000 per year for 25 years at 14% interest? So I'm going to go back to my part A and set up one more problem that's pretty similar. So in part A, I said b of k is equal to 1 plus I. In this problem, I is 14%, so this is going to be 1.14. 1 plus I times b, k minus 1. And then I had plus q, which was the amount I was depositing. So now we're thinking of, I've borrowed some money, and this is the amount I'm paying back. So I'm paying back $5,000 every year. So my q is going to be 5,000. And the question is, what is the maximum loan that I could take out if I could afford to pay $5,000 a year for 25 years? So how do we turn this into this type of problem? So again, I'm going to think of the associated homogeneous recurrence relation. B of k minus 1.14 times b k minus 1. And that has characteristic equation a minus 1.14 equals 0. So a is equal to 1.14. So I can say that this will have a homogeneous solution of the form some constant b times 1.14 to the power k. Then the particular solution, again, the function on the right-hand side, if I moved the bk minus 1 term over, would just be the constant 5,000. So I'm going to assume the particular solution is of the form some constant d, and then plug it into the recurrence relation. I get d minus 1.14d is equal to 5,000. And I'm solving for d, so that's d times 1 minus 1.14 is equal to 5,000. So d is equal to, again, negative 5,000 over 0.14. And just like last time, I think it's a little bit easier to work with fractions. So I'm going to, off to the side here, I'm going to note that 0.14 is 7 over 50. So 5,000, negative 5,000 divided by 7 over 50 is equal to negative 5,000 times 50 over 7. So this is equal to minus 250,000 over 7. But if you prefer to just leave it in this form, that's fine. So I'm working with this as my constant d. Then I'm saying the solution to my recurrence relation should be some constant b times 1.14 to the power k minus 250,000 over 7. So here's where I need my initial conditions. This is a loan, and the thing that I'm trying to solve for is the amount of the loan. So I'm going to say that b of 0 is, I'm going to call it capital L for the amount of the loan. And this is exactly what I'm trying to solve for. So b of 0 is equal to L, and b of 0 is little b times 1.14 to the power 0 minus 250,000 over 7. So this is b minus 250,000 over 7. So that gives us that b is, little b is L plus 250,000 over 7. So now I'm going to say that b of k is, I'm going to replace little b by L plus 250,000 over 7. That's times 1.14 to the power k minus 250,000 over 7. So this is the solution to the recurrence relation. I'm going to use it to answer the question that was asked, which is, what is the maximum amount of the loan if we can afford to pay back $5,000 for 25 years? So the way I'm going to translate this is I'm going to say that after 25 years, I want this to be 0 because I want the loan to be paid off. So I'm going to say b of 0 is, b of 25 rather, is equal to 0. And that's equal to L plus 250,000 over 7 times 1.14 to the power 25 minus 250,000 over 7. And at this point, it's just a matter of manipulating it and plugging it into our calculator. So we can say, then I'm going to add 250,000 over 7 to both sides. That's equal to L plus 250,000 over 7 times 1.14 to the power 25. Then I'll divide by 1.14 to the power 25. So 250,000 divided by 7. And then this whole thing divided by 1.14 to the power 25. That's equal to L plus 250,000 over 7. And then I'll subtract 250,000 over 7 from both sides. So I'd end up with something like L is equal to 250,000 times 1 minus 1.14 to the power 25. All of that divided by 7 times 1.14 to the power 25. And that's going to be approximately 34,000, and it's coming up negative because the problem told us that the amount of the loan should be negative, and we're paying it back up to zero. So $34,364.64. So that should be the loan of $34,364.64. And that is the answer to this question and how we can use these recurrence relations to think about the interest rate problems. Now I know I went through the algebra there at the end a little bit fast, so again, if you need to go back through and rewatch the video, I would recommend working this out by hand and confirming each step that I did. But this will be the solution to the problem, and this is the final problem on this lecture note. And this is the final lesson in our module on recurrence relations. So we'll go ahead and stop the video here. And in our next module, we'll learn more about inclusion and exclusion.